So this is the hydroxylation system that takes the phenolic in the pollen and converts it into the glyoxal, methyl glyoxal, and dihydroxyacetone type polymeric materials. So as the hydroxy radical is generated through a photo-Fenton chemistry, this is a light-sensitive system that's involved in pollen maturation in the maturation of Manuka honey, leading to MGO formation and the release of MGO from the release of the polymeric glyoxal from the pollen. So this is all part of pollen germination, the generation of CO2 in water. And you can consider it really a way of producing the fluid and the expansionary pressure inside of the pollen grain in order to produce that pollen tube as part of the fertilization. Getting the egg and the sperm to come together requires a pollen tube to be generated. And this physics, the physics which involves light and photo-Fenton chemistry using iron, is an appropriate way that has evolved in order to give that expansionary pressure and the fluid necessary for the migration of the sperm down through the pollen tube. And then the hydroxy radical system is actually involved in breaking open the tube to allow the sperm and egg ovule to come together to form the embryo. So the hydroxy radical system is intimately involved in fertilization. It's intimately involved in the production of an embryo. And as you can see, this system returns biological molecules back into CO2 and water. And this is also occurring in apoptosis, pre-programmed cell death, turning biological cells back into CO2 and water. So it is also happening within us, within our cells, as part of death and regeneration. So it's a very interesting light-mediated physics that happens at nanosecond speed. So it's a billionth of a second. It's very fast. The hydroxy radical doesn't last long. And with the coordination of the ion to the aromatic ring, and then the coordination of the hydrogen peroxide to the ion as in the reduced form, we get that reaction to produce the hydroxy radical. And because it's not lasting long, it's only lasting a nanosecond, it hasn't got a chance to migrate away from the ring. It actually just reacts with the first thing that it comes across, because it's that reactive. It's that most potent oxidative biochemical known. So that hydroxy radical hydroxylates the ring. It opens it up. It doesn't do a massive amount of damage, because the damage is localized to the point in which it is created, and that is due to the coordination of iron in the aromatic ring system. So it's a beautiful localized oxidative system for the generation of CO2 and water for pollen tube formation. We've kind of had this idea that the hydroxy radical is incredibly damaging because it destroys all biological molecules, and therefore we should eliminate it through the use of antioxidants. But what this really shows is that it's critical. It's so critical in our apoptotic pathway, in our phagocytosis pathway. It is necessary, and it's not the bad boy as it's been kind of presented to be in scientific literature, because it is only lasting such a short amount of time. It doesn't go on a rampage to destroy things. It actually acts locally to break down biological materials in a recycling system. So the hydroxy radical regenerative recycling system is really what's important for breaking down old cells back into CO2 and water. And if we're not removing old cells using the hydroxy radical regenerative system, then we are aging. Our biological age will increase. I know that sounds incredibly counterintuitive, considering the amount of literature that suggests antioxidants are beneficial and they should be supported within our body, and we have antioxidant systems to protect us. I'm saying in the right place and at the right time, the hydroxy radical is key to mediating apoptosis, pre-programmed cell death, which is important in the biological regeneration system, taking old, breaking it down into CO2 and water, and releasing energy in that process in order to regenerate and revitalize. Thanks.